Hello everybody, today we're moving on to 3.4. In the previous video, we talked all about growth models, exponential growth. And so today I want to switch and talk about exponential decay. How do exponential decay functions work? If we think about the graph of an exponential decay function, it's the same thing as a growth function, just flipped. So how do decay functions work? Well, if you remember from the previous video, I can write exponential equations in this form. And the reason why is because the growth rate, or the rate at which the exponential function changes, is proportional to the function value. Well, what if I put a negative in front of my constant of proportion? Is this growth rate still proportional to the function value? It is. It's just now proportional in a negative way. So what does this tell you about your growth rate? What does this tell you about my rate of change if there's a negative right here? This means that the rate of change is always negative. And this is what gives me a exponential decay function. But what's cool about decay functions is they use the same exact equation as we used for the growth function. The only difference is what's going to be true about k. K is going to be less than 0 for decay functions. But you might be thinking, but wait a second. We learned, when we first learned about exponential functions, that in order for it to be a decay function, the base of the exponential function needs to be less than 1. It needs to be between 0 and 1. And e, of course, isn't. E is 2.7 something. So how can this be a decay function if e is greater than 1? Well, the reason why is if k is negative, you'll also see decay functions written with the negative up there. And if I just isolate that e to the negative, I can use my exponential properties to rewrite this as e to the negative 1 raised to the kt. What's e to the negative 1? Remember, what does a negative exponent do? It flips it and makes it into a fraction. And so this gives me this, 1 over e raised to the kt. And tell me about 1 over e. 1 over e is less than 1. And so that's why this still ends up being a decay function, even though it's initially written with a base that's bigger than 1. This is still a decay function because the exponent's negative. That's what makes this a decay function. Now, there's lots of really cool situations that you can actually model with decay functions. And that includes radioactive decay. This is modeled with an exponential function. Carbon dating, which is very closely related to radioactive decay because you're looking at how carbon is decaying in certain isotopes. We're still going to talk about a financial model, and so we're going to talk about something called present value, which is still dealing with interest but looking backwards. Drug concentration is another great example of exponential decay. And cooling objects that cool down, you can model using an exponential function. Why? Why can we model all of these with exponential models? And the reason why is, if you think about radioactive decay or cooling objects, the hotter an object is, the faster it'll cool down. But then as it gets cooler and cooler and cooler, the rate at which it cools down slows down. And so we still see that proportionality between the rate of change and how large the amount is. So let's focus on these first couple for a little bit, because in these situations, in these contexts, we often calculate something called half-life. And the idea of half-life is how long does it take before the value is half of what you started with? Well, what does this kind of sound like? This kind of sounds similar to doubling time. This is just the opposite of doubling time because we're looking in the other direction. How long does it take for something to be half of its original value? So this is kind of the decay version of doubling time. It's this idea of half-life. And so just like doubling time didn't depend on your initial value. The same is true for half-life. Half-life doesn't depend on your initial value. And the formula for half-life is actually very similar. So we can use t for that time value, but this time I'm going to do t sub 1/2 because this is the half-life. And to calculate your half-life, you just do the natural log of 1/2. Notice, since it's half-life, it's the natural log of 1/2 instead of the natural log of 2 divided by rate of change. So it's a very, very similar formula. But what's interesting about this is if you plug in natural log of 1/2, because 1/2 is less than 1, this actually ends up being a negative value. But because this is a decay function, what should be true about k? K will also be negative, and so you'll still end up with a positive amount of years, a positive value for your half-life, because both of these values are negative. Next, let's talk present value. One of our big examples of exponential growth that we talked about was interest, right? If you have a loan or if you have an investment, you can earn interest, and that ends up being exponential growth. Well, present value is the decay version of this. Present value asks the question, how much will I need to invest now to have a certain amount of money in the future? And so it's really just calculating interest backwards, which gives me the equation P, the principal, right? The amount that I'm starting with is equal to your actual amount, your future value, a lot of times we call that your future value, times e to the negative RT. So it's the same exact formula, except we're switching places of your final value and your starting value, and we're making the rate negative because we're working backwards. So that's present value, and it's another example of exponential decay. Last, cooling objects. So cooling objects is another really interesting example of exponential decay. But with cooling objects, there's a little bit more complicated of a formula. In fact, we have something called Newton's law of cooling. And it follows this formula of capital T equals A times e to the negative kt plus c. A lot of different variables here, but we're going to talk about what each of these variables are. First of all, we're going to use capital T for temperature. Okay, makes sense. This is measuring the temperature of an object, so T represents the current temperature. Little t is still time. K is your rate, and that will often just be given to you because different objects cool off at different rates, right? Metals hold their temperature better than plastics, I'm of course not a physicist or anything like that, but different objects cool off at different rates. C represents the ambient temperature or surrounding temperature. And A, what does A represent? Well, recall with exponential decay functions, they approach zero as t goes to infinity. My exponential decay function will approach zero. So what's going to happen with this? This whole term right here will eventually approach zero. Leaving the object, you'll notice leaving the object at the surrounding temperature. So what do we want to approach zero? What is this A? The A represents the difference in temperature. Between what? Between the object and the surrounding temperature. So mathematically, I could express this as the temperature at time zero, so T sub naught, minus the surrounding temperature. And that'll give you that A value. And that's Newton's law of cooling. So a really interesting way that exponential decay functions are used to just model stuff that's happening every day. Awesome. But those are some really cool examples of ways that exponential decay is used. So try out a few of these on your homework, and then I'll be going over a couple in the examples video. Good luck, guys.